Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on electricity and magnetism. We have been discussing about the concepts related to electrostatics in this part of the lecture series. In today's lecture, we are going to learn about the energy stored in a capacitor. Let us see the session outline for today's lecture. In this lecture, we are going to learn about the energy stored in a capacitor, the energy density in a capacitor or electric field, the change in energy due to introduction of dielectric material in a capacitor under two conditions like charge remaining constant and potential remaining constant, and also the loss of energy due to sharing of charges between two capacitors when they are connected with same polarity and also with opposite polarity. So, we are going to learn about mainly the energy related to a capacitor. We will have to get an expression for the energy stored in a capacitor in terms of known quantities. In one of the earlier lectures, we have come across the expression for force that is existing between the two plates of a capacitor. What is a capacitor? Capacitor is a geometrical arrangement of conductors which are having the oppositely existing charges on the two conductors. Because the two charges are opposite in nature, there is a possibility for an attractive force existing between the two conductors. Let us take a parallel plate capacitor. If it is a parallel plate capacitor, one would have got positive charge, the other one would have got the negative charge. The two charges are now separated by a distance. So, definitely there will be a attractive force existing between them. So, against such an attractive force, the two capacitors are kept at a distance. So, there is a potential energy involved in that, the electrostatic potential energy. If you have a dielectric material, what will happen? The dielectric material is preventing them from coming in contact. So, we have to visualize as if the two charges are separated by a distance. So, in any such separated charge systems, there is energy associated with that. So, if we do it for the capacitor, we will get the expression for the energy that is stored in a capacitor. When you say energy, it is the electrostatic potential energy that is existing in a capacitor. So, we will try to go ahead with our discussion by taking a parallel plate capacitor, which is the simplest form of capacitor for our discussion. So, we have two parallel plates marked here as A and B. Here this is positively charged, this is negatively charged. Let Q dash be the charge on the capacitor at any instant and V the potential difference between the plates. The work done in charging the capacitor by dq dash, a small value dq dash, we originally charge it, right. When we want to discuss about the energy involved, we need to consider about the work that is done in charging the capacitor. So, we first take the infinitesimal amount of charge, a small charge, that is what is taken here as dq dash. This dq dash is the charge that is kept on the capacitor at an instant. V is taken as the potential difference. So, what is the work done? The work done is also taken as dW. So, work done is potential multiplied with the charge. What is the charge that is being placed at that instant? It is dq dash. So, small work done for the transfer of dq dash is written here. We can write the V as q dash by C, because this is the expression for the potential. We know the capacitor is C is equal to q by V. With that we are writing this expression. Now, we want to find out what is the total work that is done in charging it from 0 to q. The q dash is an intermediate value only, but we want to charge it up to q. So, we integrate this expression, we take the constant C outside, 1 divided by C is taken outside. So, when we integrate and apply the limits, we get this expression. Finally, we obtain the work done is of q square divided by C. So, this seemed to be the work that is done in charging a capacitor to a value q from 0 charge to the charge q, that is the fullest charge present on the capacitor. This work done is stored as potential energy in the capacitor. So, we can directly take this work done expression as the energy expression itself, because work and energy are equivalents. Shall we take that as the energy stored? We can even use the term U for it, right? We use the letter U for the potential energy. So, this work done is stored as potential energy in the capacitor. So, this becomes the expression for the energy that is stored in a capacitor. What appears here? Only two terms. We have C, Q and V as the terms here. What are they? They are the electrostatic quantities. C is equal to Q divided by V. So, we have three terms C, Q and V, but in the expression we have only two, Q and C. So, we can replace any one with the expression here. So, if you rewrite, we get the other equivalent expressions for energy stored. We can write it as of C V square. Here Q is not there. In the earlier case V is not there. In this case Q is not there, and here C is not there. So, we can write it in terms of the Q and V also, of Q V. When you have a look at this expression of Q V, have you come across this Q V already? The charge and the potential difference. When we place a charge in a potential of V, there is a energy associated to that, that is QV, full QV, right. So, energy, I would like to write all that and give a small explanation for what is happening in that case. See, the potential energy stored on a charge when it is placed on a at a point where the potential is V, it is Q multiplied with V. This expression we know, but here of comes 1 divided by 2. So, what happens? Only 50% of the energy is stored as potential energy in a capacitor. What happens to the remaining 50%? 1 divided by 2 is 0.5. So, 50% if you do that. What happens to the remaining 50%? While moving the charges, there is a possibility for the current to be set, because movement of charge is current. So, that current would have dissipated in the form of heat energy in the transfer process in the wires. The Joule heating would have taken up the 50% of the charge. So, only the 50% of the work that we do, the typical work that we do is stored as the energy. The remaining 50% goes as waste, as the form of dissipative energy. It is not stored. So, we finally have the expression of QV as the expression for the energy. It is in the three expressions. Now, what will happen when we want to talk in terms of the energy associated with the capacitor? There is electric field also existing. So, we can also say the potential energy is stored in electric field. Where is electric field? It is existing between the two plates. So, we can try to bring in the electric field also into the expression, and we can make one good statement that energy is stored in electric field also. Instead of saying capacitor, we can say in the capacitor electric field is existing. So, there is energy stored in electric field. We can even get an expression for the energy density, which is a very familiar expression. Let us see what it is. Energy stored for a parallel plate capacitor, if we do, we write it with this expression of CV square, and for C we substitute, it is epsilon naught A divided by D. So, with that, when we go ahead with the simplification, the expression for electric field between the two plates is potential divided by the distance of separation. So, instead of this V, we bring in the electric field by suitably modifying the terms. So, we multiply and divide with D and write V square by D square as one term. What is this V divided by D? It is the electric field. So, electric field square is written here. So, we have brought in the electric field term in the energy equation. What about this A and D? A is the area of the plate, D is the distance of separation. So, this becomes the volume. So, if we bring the AD, which is the volume, to the denominator here, it is the energy stored per unit volume. So, we have that expression also here. The energy stored per unit volume in electric field E is given by this expression of epsilon naught E square. So, it is denoted as small u here. Small u is the energy stored per unit volume in electric field. See, when we write this, no other term is existing. It is only the electric field and the permittivity of the free space. If it is a medium, that medium's permittivity or the dielectric constant K or permittivity, relative permittivity epsilon, any one we have to write. So, what is the conclusion? If there is electric field existing in space, there is energy associated with that. The energy stored per unit volume in the electric field is given by the expression of epsilon naught E square. This is not only true for the electrostatic field, it is also true for the electric field. The electromagnetic waves, they carry the energy, no? Even for that electric field also the same expression is true. That is why that electromagnetic energy is able to travel with its energy in space. That energy is being carried by the electromagnetic wave itself. Similarly, the magnetic field also will carry the magnetic field energy, that also will be present, which is beyond the scope as far as this course is concerned. If you are interested, you can go ahead and learn about all of them. Now, we will stick on to what is given in our curriculum. We have got an expression for the energy density for an electric field. Now, we will try to use this expression further to find out the effect of the dielectric material when it is introduced into the capacitors. What about the energy change that is happening in a capacitor by introducing the dielectric material? We will go ahead with the discussions. Dielectrics in capacitor. When a dielectric material is introduced in a capacitor, the capacitance increases. If the dielectric material fully occupies the space between the plates, the capacitance increases the dielectric constant times, the K times. K here is denoted as epsilon r also in some of the expressions, either K or we can mark it as the relative permittivity, both are one and the same. It is achieved by the decrease in potential or increase in charge, or by both depending on the condition. The energy stored in the capacitor changes after introducing the dielectric material. It is studied under two conditions, which we are going to see. What will happen when we introduce the dielectric material? When the charge remains constant and potential remains constant, like that we will go ahead with the discussion. When the charge remains constant, what is happening? The capacitor is charged by connecting the terminals to a battery. So, if the battery is disconnected, the charge remains the same in the capacitor. So, the energy without the dielectric material is given by this usual expression which we have been discussing. It is of q square by c. So, this is in the absence of the dielectric material, when we do not have that. When we introduce dielectric materials, what is likely to happen? We will have a visual here to understand the effect. So, energy with the dielectric material. Let a dielectric of constant K and thickness D and area, that means it is going to fill the space between them fully, be introduced to fully fill the space between the plates. What happens to the energy now? It is given as U dash. So, let us suitably modify the equation. U dash is of Q square divided by C dash. What is C dash? The C dash is an increased value now. How much it is increased? K times C, right? K times it is increased. With these we have already learnt. So, that is why I am directly writing the relation. The energy decreases by a factor K. So, when we introduce the dielectric material, which is here, I have to show it to you. So, when we introduce the dielectric material into the dielectric into the capacitor plate, we have the dielectric material here. So, what will happen when we introduce? The energy is getting reduced, it is 1 by K times getting reduced. This also is important. What is the K value? K value is always greater than 1. That means 1 divided by K is a value always less than 1. That means energy U and U dash, if you compare, U dash is always less than U. So, by introducing the dielectric material, the energy of the system is getting reduced. What is the logic? A system always prefers to be in the lowest energy. As far as potential energy is concerned, lowest potential energy it tries to exist. So, what will happen? The dielectric material is readily pulled in to the capacitor plate. See, that is why the force F is marked here. As soon as we introduce the dielectric material, there is a force that is pulling it inwards. So, it tries to move inwards and fully occupy the space. This is the later stage of the thing. This is how the dielectric material will get pulled inwards. It will completely occupy the space between the two plates. Finally, how it will exist? So, finally, it will completely occupy the space like this. Leave alone this part, it will fully occupy the space. Because once the dielectric is drawn inwards fully, the energy is getting reduced. System prefers to be in the lower energy, right. So, there is a pulling force, the dielectric is very well seated into the plates. Now, we will do the discussion for the other case. When the potential remains constant, when we introduce the dielectric material, what is likely to happen? Let us have that as the case for discussion. So, this is the case. It is clear that the energy, this discussion I have already given. So, the energy is getting reduced. How much it is getting reduced? All that, the difference is shown here. Because of the decrease in the energy, the dielectric is drawn into the capacitor. Now, as I said, we will take up the next case. When the potential remains constant, what is likely to happen? When the battery is kept connected to the capacitor plates, the potential difference between the plates remain constant. In this case, the battery can supply or receive charge to and from the capacitor. So, this point we have to keep in mind. Because of the presence of the battery that is connected, there is a possibility for the change in the charge. The potential will remain same, but the charge can vary. Either the battery can take the charge from the capacitor, or it can supply the charge to the capacitor according to the system, according to the case. So, we will see what is going to happen. So, energy without the dielectric material, if we do, here we are taking the capacitance C V square of C V square expression for our discussion. This is in the absence of the dielectric material. Now, when the dielectric is introduced, what is likely to happen? The energy with dielectric material, let the energy be U dash before the dielectric is introduced, and see accordingly there is a change we are giving for this. C becomes K times C, C dash is K times C. So, what happens in this case? Hence the energy increases by a factor K. Comparing earlier, it was in the denominator, K was in the denominator, refer the earlier expression. Now, K appears in the numerator, so it increases. The conclusion is here the gain is happening. This energy is supplied by the battery that is connected to the capacitor. Hence, the dielectric is not rejected by the capacitor. We may have an idea. See, when the potential remains constant, the energy is increasing. So, the system will not prefer such an increase. So, the dielectric will be ejected. Will it happen? No. The battery will do the additional work, that is stored as potential energy, that is increasing the potential energy. So, in this case also the dielectric is safely kept inside, because the potential source is doing the work. So, we have seen the two cases of introducing the dielectric material in a capacitor. Now, what will happen if we rewire the capacitor? When we charge one capacitor and connect another capacitor, uncharged capacitor or charged to a different value, what will happen because of the rewiring? That is called the rewiring of capacitors. Let us see quickly what does that mean. Let two capacitors C1 and C2 be charged by voltage sources V1 and V2 to charges Q1 and Q2 respectively. There are two ways of rewiring them. They are with the same polarity, with opposite polarity. In the same polarity, the positive plate of C1 is connected with the positive plate of C2, and similarly their negative plates are also connected. In the opposite polarity, positive plate of C1 is connected to the negative plate of C2 and vice versa. The negative plates are also connected. So, these two cases we will take up for discussion. What is the title for this? It is rewiring. After the two charged capacitors are connected with the same polarity, opposite polarity, what is likely to happen? Case by case we will see. See, in this case with the same polarity we are doing. Let the rewiring is done with the same polarity with the two switches S1 and S2. We have two switches to connect them. So, here we have the capacitor C1, here we have the capacitor C2. They have separate charges. Q1 is on the first capacitor, Q2 is on the second capacitor. So, when we close the switches, what is likely to happen? Now, from one the charge would go to the other. We do not know whether the Q1 has given charge to Q2 or Q2 has given charge to Q1, but one thing is for sure, when the rewiring is done, the total charge remains constant, right. The charge will not change. The Q1 and Q2 individually the charges will not get cancelled, because it is the same polarity connection. So, what is the discussion we have for this? Before rewiring, the charges are given with these expressions. So, the total charge is this should remain the same, the Q1 and Q2 should remain the same even after rewiring. So, we have written the expressions here. The total charge will be the same even after rewiring. So, now because of the charge sharing, the two charges are written as Q1 dash and Q2 dash, but even in this case also the summation is Q only, because charge has to remain the same because of the same polarity connection. So, after rewiring, the capacitors are connected in parallel. Thus, there is a common potential found existing between the two capacitor plates. Have a look at this one. See, the two capacitors are now connected in parallel. So, there must be a common potential. This is the expression for the common potential. The change in potential energy is also likely to happen in the case. So, this is the energy for the first case of the two capacitors. Now, after, so the initial energy is the summation. The final energy if you take, it is of C V square. What is the C? This is the common potential. C is the common capacitors and V is the common potential. So, when we plug in the values, I have not shown the mathematical simplification, but would like to give the final expression. When we do that and subtract the initial and final, no, the final is subtracted from the initial, we get a positive value. That means, when the rewiring is done, charge flows from one capacitor to the other capacitor So, there is a loss in potential energy because of Joule heating. That is why the initial energy is found to be higher and the final potential energy is found to be lesser. When we find the difference, we are getting the positive value. So, let us make the last statement. This loss in energy appears as heat in the connecting wires, partly as light and sound also with the sparking. There is a possibility when we rewire at the time of closing the switches, there is a possibility for sparking, sound and all that, no, discharge when it is happening. Such possibility of loss is there in the rewiring situation. So, we have come across the loss in energy. What will happen when they are connected in opposite polarity? That will be a easy run through for us. So, let us quickly take up the case for discussion. Now, it is connected in opposite polarity. Now, also there is a common potential when they are connected in opposite polarity. So, opposite polarity is shown here. The first capacitor is like this, second capacitor is kept in the opposite polarity ready for connection before rewiring. Once the switches are closed with the opposite polarity, they are connected in parallel. Now, what will happen? There is a possibility for charge loss because the positive is connected to the negative. So, there is a possibility for annihilation, all that has to be kept in mind. What is done here? Before rewiring the charges, the two charges are given like this. Why there is a minus charge shown here? Because this is going to be connected to the positive Q1. So, we write the expression for total charge. After they are connected, the charges are Q1 dash and Q2 dash. So, after rewiring, the capacitors are connected in parallel. So, we try to find out the common potential. The common potential is also found here, the charge Q divided by C1 plus C2. This is a common parallel connection value. So, when we do that, we get this as the final expression for the common potential. We have a negative sign here when we compare it with the earlier expression. Because of that, what is happening? We want to find out the energy change. So, when we find the energy change, the initial energy for the two capacitors and the summation is shown here. The final energy is taken like this of CV square. We have to substitute for the C, which is C1 plus C2, and the common potential. So, when we plug in the values, we get this as the expression. The only change is in the sign that is appearing here. In the earlier case, it is V1 minus V2 the whole square, but in this case, it is V1 plus V2 the whole square. So, all the more the energy is lost because the annihilation of charge is happening. This loss in energy appears as heat in the connecting wires, partly as light and sound along with sparking. The same thing is happening, only the expressions are different. So, we have seen the energy associated with the capacitor and the introduction of dielectrics and rewiring, all that we have seen elaborately. Shall we see the summary of today's lecture? In this session, we have seen the energy stored in capacitor, energy density in a capacitor or in electric field, change in energy due to introduction of dielectric material in a capacitor, when charge remains constant and when potential remains constant, and also we have seen the loss of energy due to sharing of charge between two capacitors with same polarity and opposite polarity conditions. We will test our understanding of what we have learnt in this lecture by answering these questions. Derive the expression for the energy stored in capacitor. Explain the change in energy due to the introduction of dielectric in capacitor while charge remaining constant and potential remaining constant. Discuss the loss of potential energy in two capacitors due to sharing of charge, that is rewiring with same polarity and opposite polarity. With this, I would like to wind up this lecture and see you in other lectures with other concepts related to electrostatics. Thank you for watching this program.